So we want to take a look at capacitors. And to begin that process, we're going to start by looking at what we call the charging of a capacitor and then the discharging of a capacitor. Now, the thing of it is, something that's new when it comes to capacitors is now we have time-dependent responses. And so we have to introduce this notion that things are going to change with time. The way we begin that process, one important thing we do is we introduce this switch. And I'm going to title it SW. So SW just simply refers to the switch. And we have to pay attention to what position the switch is in. When it comes to time dependence, we're going to express the voltage on the capacitor as VC of T. A couple of things that I'd like to point out about that is we're using lower, if you notice, we're using lower script or lowercase script letters to identify that. In the electrical field, that always identifies a time-dependent function. And so we write it as VC of T. So that would stand for the voltage across the capacitor C as a function of time. A couple of other important things we need to take a look at when it comes to capacitors and we need to come to grips with is before a capacitor has any charge on it, what's going to happen is we're going to close the switch at what we call time equal to 0. And so we need to get used to taking a look at time-dependent functions. In this case, VC of T. And getting used to this notion that we can stop time. Okay? So right now, that's what I'm going to do. I'm going to stop time at T equal to 0. Okay? And explain a couple of things. When I do that, at time equal to 0, we're going to close the switch to position 1. Okay? And we end up with a circuit that looks like this. And right at that point in time, our capacitor, for a brief moment, looks like a short circuit. So I'm just going to erase that capacitor. And I'm going to replace it with a short circuit. As a result, the voltage on the capacitor at that point in time is 0. So I might write that as VC of 0 equal to 0 volts. Okay? And for a brief moment, we need to grasp the notion that time isn't changing. It's concerned to our circuit right here. Time is at a standstill, okay, for this brief moment. What happens next then is we want to think about what's going to happen beyond what we call 5 tau. And I'll explain that, but when we are past, when we're at or beyond 5 tau, which is a time, and I'll explain that in a minute, we are at what's called steady state. And when we reach steady state, and I'm just going to go ahead and put that out here on our time, what's going to happen once we reach steady state for a capacitor? is it's going to be fully charged, and after that time frame, the capacitor now looks like an open circuit. But it's a rather interesting open circuit. Capacitor now looks like an open circuit charged to the open circuit voltage. So what would that be? Well, if we redraw the circuit with that open circuited, there's our switch closed, 8K ohm resistor, and an open circuit here where the capacitor would be, and if I put my voltmeter on there, I would measure 20 volts. Now those two things are important because what's going to happen is VC of T is going to go from 0 volts to greater than 5 tau, or steady state, V open circuit. And those two things are what we want to know. We want to know when the switch changes state what the voltage is. In this case it's 0, and after steady state, or after 5 tau, what the voltage is. Okay? Now, let me explain tau a little bit. For a capacitive circuit, tau is what we call the RC time constant. And for capacitors, it's simply the resistance that's connected in the circuit. I'll explain how to calculate that in a second. Times the capacitance. So in this case, there's an 8K ohm resistor and a, what was our capacitor? 12 microfarad. And a 12 microfarad capacitor. Give us a tau. And this is just for the charging phase of 96 milliseconds. When I run that out, I get 0.96 in the units per seconds, giving us 96 milliseconds. Okay, so now that we have established the open circuit voltage and what a capacitor looks like at t equal to 0, okay, with our circuit that we're using. Remember, this is our original circuit, and we're only looking at the charging phase right now with the switch in position 1. We've established what tau is. We have looked at what the capacitor is going to look like after 5 time constants when it's an open circuit, and what it looks like at t equal to 0 when it looks like a short circuit. Now, to introduce what these time domain expressions look like, what we do in this class is I simply give you the equation for what the voltage across that capacitor is going to look like. It's a time domain function. It's kind of ugly here, but what you're going to see is we're headed to V open circuit, which was, I believe, 20 volts for us here. Yep. So I'll write that in here, 20 volts. And then we're going to take a quick look at how we establish the current, and this part of the current right there, E over R. And then we're going to also take a quick look at what the voltage drop across the resistor is. Now, what I want you to comprehend is that it simply follows the current multiplied by the resistance, in this case 8,000 ohms, and that's just an expression of Ohm's law. So that's an expression of Ohm's law, and kind of a bringing into the equation the time, what we call this time domain format, or now our signals or our responses are dependent upon time. Okay, unlike what they typically are in DC, where they're just constant. Okay? So let's take a look at VC first. So let's calculate a few points. VC of T is going to be equal to that open circuit voltage was 20 volts times 1 minus E to the negative T over tau. And it's important that you learn how to put this in your calculator. Okay? And remember, we calculated tau to be, I think it was 96 milliseconds. That's correct. And we're going to take a look at this in a couple of different formats. So let's take a look at the time frame. Let's call it 1 tau, or 96 milliseconds. Okay. If we come over here and put this on a graph, remember now that voltage on that capacitor is headed to 20 volts. So out here, in fact, I'm just going to use my grid line. So 1, 2, 3, 4, 5. Once we get out here to 5 tau, and I'm deliberately not you're putting that on the 20 volt line because it really is an asymptote up here. It takes a long time really for it to get there, but we're like at 99.8% of that 20 volts once we get out here to 5 tau, which for us, 5 times 96 is what? 480 milliseconds, which hopefully you agree is about a half a second, right? Okay. But let's go back here to 96 milliseconds first, and let's plug those numbers in. So what would we get? We would get, I would write that as V of C of 96 milliseconds. Now, time actually has a number of 20 times 1 e to the minus 96 milliseconds over 96 milliseconds. Now, plug that into your calculator, and what do we get? If you plug that in your calculator correctly, you should get 12.46 volts. So, if we go over here, it's going to be a little more than halfway. And the first time constant, first 96 milliseconds, we're going to go from 0 to 12.64 volts. At tau equal to 2 tau, or 2 times 96 milliseconds, okay? Plug those numbers in there. You should get 20 times 1 minus e to the negative 192 over 96, and make sure you know how to do those calculations in your calculator. You should get 17.29, okay? Now, if you haven't noticed, we can calculate this, make this calculation a little bit easier just by saying, let's take a look at 3 tau. And before I forget, let's go ahead and put that number in here. So we're already up here at 2 tau. At 3 tau, we could make this 20 times 1 to the minus 1 minus e to the negative. I don't know if you noticed it, but every time if we take that exponent minus e over tau, if we say 1 tau, tau's calculated, or tau's cancel out, and it just becomes 1. Now, that's 96 milliseconds for us, okay? If we, at 2 tau, it would be 2, now there's a negative sign out there, 2 tau over tau, okay? Or that was 192 milliseconds, but it just becomes negative 2 there in that exponent. So, 3 tau, I would get negative 3 in that exponent. Plug that number in there, and I get, so you plug those numbers in there for 3 tau and 4 tau, and we go from 19 to 19.6 on up to 19.865. So up here at 5 tau, this would have been 19.865. And then 3 tau and 4 tau. And so that's what's happening to the voltage, okay? In the next video, we will we'll proceed to take a look at the current, what's happening with the current, and what's happening with the voltage on the resistor VRT. And then we'll move on to the discharge circuit.